Hi and welcome to another video. In this video we are going to solve search in rotated sorted array problem from Leetcode. In this problem in the problem statement they will give a list of numbers and a target number. We need to return the index at which the target element is present. If the target element is not present in the list, then we will return -1. This is the problem overview, but in the problem they have also specified that our algorithm should run in O of log n runtime complexity. Before that, let us understand what are all the other characteristics of the given list. So originally there is a list which is in a perfect sorted order. So without any rotation, every element will be greater than the previous element. So if you consider this array 0 to 7, if you observe, every element is in the increasing order. So this is without a rotation. Once we rotate the array by some times, then we will get this array. Let us say if we rotate the array 3 times, then 0 will move to the first, second, and 0 is in the first position. After giving 3 rotations, it will go to the fourth position. So fifth position. So 0 after 1 rotation it will come to second position. After 2 rotations 0 will come here. After 3 rotations 0 will come here. So this is the approach for rotating an array. So they have given an rotated sorted array and we need to find a target in that array. So if you consider this array or list, we cannot directly apply binary search for finding some element here because only part of the array have been sorted. If we want to apply binary search over a range, then we can do. Let us consider this range in this rotated sorted array. If you observe these elements 4, 5, 6, 7 elements are in increasing order. If you observe this range also 0, 1, 2 elements are in increasing order. But if you consider this entire range, elements are not in increasing order. If you start from 4, then we will get 5, then 6 and 7. Till this point, elements are in increasing order. But suddenly from 7 to 0, the value started decreasing. So only this range is in increasing order and this range in increasing order. So within this range, we can perform binary search to find a particular element, and within this range as well we can use binary search. So the problem reduces to finding this particular index first. So if we know this index, then we can decide, but depending upon the target value, if target value lies in this particular range, then we can start searching in this range. If target value lies in this range, then we can start searching in this range. So we have to do binary search twice here. First to find what is the index at which the minimum value is present, and next we will decide a particular range either to this side or this side. Then we will do binary search again. For deciding the index of the minimum element which is present in the list, we have to use binary search. So for that also we have to convert this array into series of trues and false. Once we have an array which consists of series of trues and false, then we know that we can use binary search to find the first true value or the last true value, or the first false or the last false. I will give some more explanation here. If you consider this array, this is the first example. So if we ask one simple question, so whether this element is greater than or equal to first element is 4, so the first value will be true. For the first value, this condition is true, that is greater than or equal to first element. For the second element also, 5 is greater than 4, so we will get a true. For the third element, 6 is greater than 4, for third element also we get true. For 7, if you consider 7 is also greater than 4, so for this position also we will get true. 0 is greater than 4, 0 is not greater than 4, so we will get false here. For all the remaining elements we get false. So once we know that if we have an array which consists of series of true followed by false, then we can easily find the first false using the binary search approach. So the first false indicates the minimum element position. So once we know this first position, then we can use binary search based on the target value. This is what we are going to do. So initially we will start finding the minimum element index. Let us initialize it to -1. So then we will start finding the minimum element index. Left is 0 and right is length of nums -1, that is the last index. Right is pointing to the last index of the list. Once we have these two pointers, then we can start binary search using that condition. So we cannot directly apply for this array, but we can use binary search to find the first false value. That first false value represents the minimum elements index. So while left is less than or equal to right, then what we can do is we can try to compute the mid. We will compute the mid, that is left plus right divided by 2. So this is the mid element. Once we know the mid, we can ask a very simple question. So we want to find the first false. So we will check whether if our mid element, that is nums of mid, is greater than nums of 0. So why are we checking this particular condition? Because if we follow this, if we ask this question at every position, this will result in a series of true and false for a rotated sorted array. That is the trick here. So if it is true, then every element to the next, that is mid plus 1, mid plus 2, will also be greater than nums of 0. So we know that if we ask that particular question, array will result into series of truths followed by false. So there is no point in every element to the left will also be true. So we have to start searching in the right. So mid will become left plus 1. Otherwise we found the first false. So we have possible main element index. Main element index is mid, but we have to keep on searching for the first false. So we'll bring the right boundary to mid minus 1. At the end of this, we have an index. If min element index is -1, that is, this condition never become true. That means we didn't find a false. If that case arises when all the elements are in sorted order, if we don't give any rotation to the array, that time that minimum element will be index 0. So what we can do is we can simply start searching over for the search range left. If that is the case, then we know that minimum element index is 0. Let us keep this way only. Otherwise we have a valid minimum element index. So now we have a range from 0 to minimum element index. This is 1 minimum element index -1, and from here to, and the second range is from minimum element index to len of nums -1. So we have these two ranges now. So we need to determine in which range we have to perform the binary search, because either we have this range, this is a valid range, this is the first range 0 to minimum element index -1 index, and this is the second range, that is minimum element index to last index. So we have to choose a particular index based on the target value. So how can we do that? So if our target is greater than or equal to if our target is greater than or equal to element which is present, we need to check our target is greater than or equal to this range, right? Whatever the thing that we are considering, nums of minimum element index and target is less than or equal to nums of len of nums minus 1. This is the last number. So if that is in the range, then once again we have to start doing the binary search. So once again we will take left as minimum element index and right as len of nums minus 1. From here we have to do the binary search again. So while left is less than or equal to right, then we have to keep on searching. We will compute the mid will become left plus right divided by 2. So we are searching in an increasing order range. So if our nums of mid becomes the target, I think we can write it as a separate function, binary search. If mid becomes target, then we can return the mid because the index they need. If nums of mid is greater than the target, then if mid itself is greater than the target, then every element is next to mid will also be greater than the target. So we have to bring the right range to mid minus 1. So what happens if our mid is less than the target? If mid is less than the target, to the left side also there will be elements which are lesser. So we have to bring the left boundary to mid plus 1. So if we are not able to find anything in this range, then we should return minus 1 here. So else, if that is not there in that range, then we have to check whether it is in this range. We will consider this range here, 0 to minimum element index minus 1. If target is greater than or equal to nums of 0 and target is less than or equal to nums of this particular index, that is minimum element index minus 1, minimum element index minus 1. So if you have that range, and that time left will become 0 and right will become minimum element index minus 1. So once again we will do the same thing here. I think I should have written this using some kind of function, but let's see. Okay, if we don't find a valid range, then it is not possible. Anywhere present we will just return minus 1. I hope this makes sense. This has a lot of repetitive code. We can put that inside a function, but how we are deciding the range, that is important. We are doing binary search twice. We will end up doing it twice because only one of these if cases gets executed. So let us see if it passes the initial test cases. Okay, we are getting some time limit exceeded. Let us see what mistakes we have done. So if nums of mid is greater than nums of 0, that means the mid element is greater than 0, we got a true. So every element to the left will also be true. So here left should be mid plus 1. We made a mistake here, left should be mid plus 1. Now let us submit this solution again and check that was a logical mistake or typo. Yes, as you can see here, this solution is passing the initial test cases, and let us see if we can discuss about time complexity. Before submitting the solution, we will check the time complexity as well. For time complexity, initially we will do binary search over the range. So this is O of, if there are n elements, that is log n, and at worst case we will not be able to find the minimum element index, we may get a 0. So at that point, once again we will do binary search over that particular range. So it becomes O of log n plus log n actually. O of 2 log n, if we can reduce the constant, if we can get rid of the constant. So this is our time complexity, O of log n. What is the space complexity? For space complexity, we are using some variables left, right, min, element, index. These values will not, the memory consumed by these variables will not increase with the input size. So we have a constant space complexity and logarithmic runtime complexity. Let us submit this solution and check whether it passes all the test cases. Okay, it is failing in some test cases where input range is 0 and 1. Okay, this is interesting. So what happens if we get a 3 and 1? If we get a 3 and 1, we get let's print and get to know like what is the minimum element index we are getting. So print min element index, and we can check where we are going wrong. So we print that thing. On the standard output we are getting 0. That is okay. Why we are getting 0 here? It should be 1 because minimum element index is 1 actually. Instead of 1 we get 0. Why is that? So here left is 0 and right is 1, and mid becomes 0 and left becomes mid plus 1 actually. So we will print here. Oh, I think along with problem solving, debugging is a nice skill to have. For we will print left equals left, right equals right, and mid equals mid. This way we will get to know like where we are going wrong. So it is failing here. Initially left is 0, right is 1. It makes sense. Mid is 0. So okay, mid is 0 and the nums of mid is greater than. Okay, we missed a simple if case here. We should check not just the greater than or equal to, because that is what we are checking here. For reducing array to list of true and false, greater than or equal to first element. So let me submit this solution and check whether it passes all the test cases now. So we missed a simple greater than or equal to sign here. Instead of greater than or equal to, we have initially written just the greater sign. Okay, initial test cases are passing. Let us submit the solution and check whether we are getting proper output or not. Yes, as you can see here, this solution is passing all the test cases. One way we can refactor this code is we can write a separate binary search function, which we are writing these things repeatedly. Instead of writing these things repeatedly, we can refactor this code into a particular function and we can use that function. So thanks for watching this video. If you are interested in learning more about data structures and algorithms, you can consider checking out other videos from my channel.